Hi everyone, welcome back to Math 112. This is Scott. Let's get started. What we are going to be doing today is starting a new chapter, Chapter 8. In Chapter 8, we'll be building on the things that we learned about the unit circle and about triangles, and turning that into a variety of other formats. It's going to be essentially taking the tools from chapters 5, 6, and 7 and applying them to new domains. So what we're going to be starting with in 8.1 is what are called polar coordinates. And here's the basic idea. So we have worked hard to understand what standard position means in this class. We know what it means for an angle, and then if we think about changing the radius from a unit circle to some other kind of circle, then we can basically describe the position of any point based on those two pieces of information. And that means we can use the standard position of a point as an alternative coordinate system to the classic XY. The basic idea here is we can use the location of a point in standard position as an alternative coordinate system. To the classic XY Cartesian or rectangular coordinates. Okay, so typically when we are talking about the coordinates of a point, we mean its x-coordinate, also called its abscissa, and its y-coordinate, also called its ordinate. Uh, but that's only one way we could categorize the points on the xy plane. So that is called the Cartesian coordinates, and that it is named after René Descartes, who was the first person to formulate it. Or it's also called the rectangular coordinate system, and it's called rectangular because the two coordinate axes are at right angles to each other. So rectangular, right angle. So here is what polar coordinates, on the other hand, as an alternative would be. So use r and theta to represent a point. So r, this represents how far from the origin we are going. And then theta, this represents in what direction. And this is in standard position. And a quick note. So r, now in this context, as a coordinate can have negative values, which would not ordinarily make sense if we think of r as being a radius, but here it can sometimes assume negative values. So r can assume negative values when used as a coordinate. And what that means is that instead of going the direction you think, it's the opposite direction. That's what negatives always mean. They always mean there's a direction that is being somehow privileged, and that the one in question is going the opposite direction. So this would mean going the opposite direction. And we'll see what that means in a second here. And as for theta, theta can have an infinite number of values for each point unless we specify a certain range, such as 0 less than or equal to theta less than 2 pi, or something like negative 2 pi less than or equal to theta less than or equal to 2 pi. And the reason for this is, as you know, you can go around and around and around the circle, and you can end up pointing the same direction an infinite number of times. So if we specify a certain range of values, then that will nail theta down. If we don't specify it, then theta could assume an infinite number of different values for the same spot on the coordinate plane. And that's just a fundamental fact about polar coordinates. Okay, so let's try this out. So plot. Let's just try example. Plot the following points given in polar coordinates. So r theta. So this is the way we write polar coordinates, r comma theta. Okay, so let's just do this over here. I'll just give a bunch of coordinates or a bunch of polar coordinates of points, and we'll just plot them here. So A, so it's 4, comma 270 degrees. And the angle in polar coordinates can be either degrees or radians. It doesn't actually make any difference at all. Say for a second one, negative 3, comma pi. And then for a third one, let's say 5, comma 5 pi over 3. And for a fourth one, let's say -3, 120 degrees. And then let's say a fifth one, 2, -5 pi over 4. And then let's say for a sixth one, -3, -3 pi over 4. And that'll be enough. All right, so let's just draw in an xy plane here, and the way we'll just do it is we'll just label each point by its letter A, B, C, and D, and so on. Okay, so let's think about this. The first one. So R is 4, and the angle is is 270 degrees. So that's going to be saying we're going from the origin four steps out in the direction of 270 degrees. So that would be directly south. So that'll be point A. All right, so for point B, what we are going to be doing is facing in the direction of pi, and we're supposed to walk -3 steps, which means 3 steps backwards. So from the origin, we moonwalk, we walk backwards 3 steps while facing the direction of pi is a way of thinking about that. So it's going backwards. Negative always means opposite direction from whatever positive would mean. Okay, now 5 pi over 3 is the direction, 5 is the distance. So 5 pi over 3, so that is down here. It's like the same as -60 degrees, or it's 300 degrees. And we're supposed to be stepping out 5 units here. 2, 3, 4, 5. And that'll be C. Okay. D. So 120 degrees, which is going to be over here, and -3. So notice that this is actually the same direction as this one down here. It's just we are going to be stepping negative direction. So we actually have 1, 2, 3. So right here is actually where D is going to be. All right, E. So -5 pi over 4. So 5 pi over 4, that would be, so that's a 45-degree one, and if we go negative, so this is pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. And we are supposed to be stepping 2 units. So it's 1, 2. And that's going to be D. And then for, sorry, E, I mean, echo. All right, and then for F, -3 pi over 4. So again, we're going backwards here, and we're going, so pi over 4, 2 pi over 4, 3 pi over 4. And then we're going actually opposite direction as well, 3 units. So it's going to be out to here. So that's what the basic meaning of polar coordinates is. It tells you which direction to walk and how many steps to take. You can think of it as like taking so many paces in each direction. But now let's talk about converting between the two different coordinate systems, because we haven't done anything all that mathematical here. So converting. Between polar and rectangular coordinates. All right, so here's some basic facts. Let's think about the same point considered in both coordinate systems. So, how far is it out? That's going to be what r is. What angle is it going to be at? That's what theta is going to be all about. So be it. Now, if we also think about the x and y coordinates here, the x coordinate represents that distance, the y coordinate represents this distance. Now let's think about the facts that we know about a point like this. So we know the angle, we know the r, which here we can think of as serving as a hypotenuse of a right triangle, or we can think of it as the classic r that we've been using for characterizing points on non-unit circles. Now, some facts. Well, first off, if I were to take the cosine of theta, that would be the same as x over r. But that in turn leads us to a more useful fact that x equals r cosine theta. So I will put a box around the ones that are going to be most useful for us. Now sine theta is the same thing, y over r, just with y instead of x. And so now, by the same token, if I multiply both sides by r, I'll get y equals r sine theta. Another important fact. Okay, good to know. Now, if I want to think about it from the other direction, what is, or let's think about another fact I know. So tangent theta is equal to y over x. And that itself is also an important fact. And then another important fact here is the Pythagorean theorem. So these are all based on SOHCAHTOA. The other major thing that gives us any kind of extra information in these trigonometric situations is the Pythagorean theorem, which is going to here mean x squared plus y squared equals r squared. Okay, well these are the 4 facts that we can use. So using these facts. Well, there are 2 directions that we might have to convert. We might have to go from polar to rectangular, or from rectangular to polar. One of these is easier and the other is harder. And what makes the difference is that in this one, for example, we can actually see what x equals if we had the r and the cosine, or the r and the theta, and we can see what y would equal if we had the r and the theta. So if it's polar to rectangular, so then we just plug in values of r and theta and the things we'd be plugging them into would be just x equals r cosine theta, y equals r sine theta. So that's actually going to be relatively straightforward. It's the other direction, though, that'll be a little bit less straightforward. So that's polar to rectangular, or polar to Cartesian. And then the other direction is rectangular to polar. So rectangular to polar. So here, find r. by using r squared equals x squared plus y squared. And then the hardest one is going to be the theta. By using tan theta equals y over x. Now, a note here. If you solve for theta using the inverse tangent, so using the inverse tangent, or the arctangent, you must determine the quadrant of the point and use that to decide if you need to adjust your theta by pi or 180 degrees. And that would mean adding 180 degrees if that was the more convenient option, or subtracting. Either one will get you the same basic situation, same basic point. So, and then if it's radians, it would be pi instead of the 180 degrees. Okay, so let's just try our luck at this. So, for example, let's say we want to go polar to rectangular. All right, what's that going to look like? So let's say first off, we have a point like 4 comma 3 pi over 2. Okay, so first off, just a note, that's r, that's theta. So always make a note, are we talking about a situation where we are given the x and the y, or are we given the r and the theta? And if, as here, we're given the r and the theta, then we just plug those into the corresponding formulas for the x and the y. So x equals y equals, and these are just both a slightly modified version of the classic definitions of cosine and sine. So x is going to equal r cosine theta, y is going to equal r sine theta. And we have both r and the theta, and so it's going to be 4 times cosine of 3 pi over 2. And that's going to be 4 times sine of 3 pi over 2. And now here we don't need a calculator. 3 pi over 2 is a known angle to us. So that's pi over 2, pi, 3 pi over 2 down here. And so that means x is going to equal 4 times the cosine, which is the x value, which is 0. So that'll be 0. And y, on the other hand, will equal 4 times the sine, which is just going to be -1. And that's going to then give us -4. So then the xy coordinates will be 0, comma, -4. Okay, so is it ever very much harder than this? Not really, not really. It's always approximately this difficult. because when you have the formulas, all you have to do is either evaluate the formulas by hand, by knowing the angle, or by calculator if it's an angle that is not known to us. So, for example, in B, let's say that we have so negative 2 comma 2 pi over 3. Now here once again, it's r, that's theta. These are all cases where we're starting with polar and ending in rectangular. Okay, well then, x is going to equal r cosine theta, y is going to equal r sine theta, and we will just let the pieces go into their appropriate spots and see what happens. So it's negative 2 cosine 2 pi over 3. This one is negative 2 sine of 2 pi over 3. And now we can just have a look at what the angle in question is here. So pi over 3 is 60, so this would be 120, which puts us just a little bit past the 90 here. So this is going to have the smaller negative x value and the larger positive y value. It's going to be negative 2 times negative 1/2 for the x. And then this one is going to be equal to negative 2 times positive root 3 over 2 for the y. Okay, so then what do those equal? Well, the 2's in the denominator will cancel with the 2's that are not in the denominator, and that'll just be equal to positive 1 in this case, the negatives cancel. And in the other case, the negatives will not cancel, but the 2's will. And so we'll have negative root 3, and so that gives us x comma y equals 1 comma negative root 3. All right. What about something like this? If we have something like negative 3.1 comma 182 degrees, then we do not have an angle that we can evaluate exactly using our knowledge about the unit circle. We have an angle that we'll have to evaluate approximately using a calculator. And so here, this is again the r, this is again the theta, and we will just let a calculator do the work for us. So x equals r negative 3.1 times the cosine of 182 degrees, whereas the y is equal to negative 3.1 times the sine of that same angle. And notice when it came to changing from these rectangular coordinates, or say these polar coordinates to rectangular coordinates, we didn't even bat an eye at the negative r. The formula is the formula. R can be positive, r can be negative. It doesn't really make any difference. We just do the same thing in either case. That's the beauty of a formula. Okay, so then we just use a calculator. And we'll just say we round to 2 decimal places. Okay, so then most importantly here, you just have to make sure that your calculator is in the mode that the angle has been given in. So if the angle is in degrees, make sure your calculator is in degrees. If the angle is in radians, make sure your calculator is in radians. So negative 3.1 cosine 182. So it's approximately equal to positive 3 point, and if I want to round this to 2 decimal places, then 9 would round up, so I'd actually round it to 10. So 3.10. Okay. And then, alternatively, we can try this with the sine. So if you just hit up on most calculators, especially calculators of this style, you can modify whatever your previous expression was, such as changing a cosine to a sine. And then here we'll have 0.11. If I'm rounding to two decimal places, the 0 would round up to a 1. Okay. So then xy would equal 3.10, 0.11. Let's see if this is reasonable, by the way, because 182, so that's pretty close to 180. So 180 degrees over here, and then if we go negative 3, so slightly past it, so that means it's going to be right down there somewhere. And then we go to the other side over here, since it's a negative value, and we look at that. Is that a reasonable answer? If it is, then that's great. If it's not, then most likely what that means is our calculator was in the wrong mode. Maybe our calculator was in radians instead of degrees. Now, what about something like this? How about 8.1, 5.2? Now, this is again the r, and this is the theta. And since it doesn't have the little degree symbol, that means it is in radians. Even if it doesn't look like one of your more familiar radian angles, usually your radian angles have some kind of pi involved. It's like 3 pi over 2, 2 pi over 3, things like that. Here, however, the fact that it has no degree symbol means that even if it doesn't look very radianish, it is. So this is radians. Now, before we even proceed here, sometimes it is a good idea, just so that you make sure that you don't make any kind of foolish mistakes, just try to guess at the approximate value that this would have. So 5.2, where is that? Well, we know that it is more than pi. Pi is 3.14. We know that it's less than 2 pi. And as far as which of these sides it's on, a little hard to say. So let's think about this. What is 5.2 divided by pi? So it's apparently 1.6. So that makes it a little bit more than pi and a half, which means we're talking about something down here. And it's going to be going down like that. So the reason why you might want to do something like that and figure out the approximate position of your point is whenever you've got these things, it's very easy to go on autopilot and just go ahead and leave your calculator the way it was and just put in the new numbers. And the problem is you have to keep yourself alert to the fact that you might have to change the mode. So here, if I'm not careful here, I just type I just type on autopilot 8.1 cosine 5.2. I calculate that away, and I get an x value of 8.06. Well, that doesn't seem very likely here. And if I try the y value, that's even less likely. So we've got a slightly positive y value and a really big negative value. So the calculation I was about to do was about to say that it was over here, which I know is not the case. I know that it's somewhere down here. I know that it's just a little bit more than 1.5 pi, which is 3 pi over 2. And so there's no way it's going to be up here like that. That's crazy. What went wrong? My calculator was not in the correct mode. So make sure your mode is right in order to make sure that your answer will be reasonable. So 3.979. That's a little bit more reasonable, not so far out there. And then for the y, that's equal to 8.1 sine 5.2. And you just calculate away. And what do you get? Negative 7.16, if I round. and that seems pretty reasonable based on where I guessed this angle would be. And if it's hard to tell where the angle would be, you might just convert it to 2 degrees because that's usually easier than radians. So then that gives my answer xy equals 3.79, comma, negative 7.16. Alright, so that's the kind of thing that can happen here, and the most common mistake you can make is probably having your calculator in the wrong mode. Okay, so let's try a new example where we convert the other direction. So, convert from rectangular to polar coordinates. Alright, so first item, let's say 0, 2. Okay, so first off, 0, 2. These are given to us in rectangular coordinates, Cartesian coordinates, meaning that the first coordinate is the x and the second coordinate is the y. These are not r and theta, these are x and y. Okay, so what's that going to mean then? So if we think about what we know here, well, actually, not circle, just draw it as a square plane. X is 0, y is 2. Well, I can actually just see what this would be right here. So I can tell this. I can tell that r is equal to 2 and theta equals pi over 2. I didn't have to actually do any calculation to find that. When it's a nice simple thing like this, we don't actually have to calculate. 2 pi over 2. So always keep your eyes peeled for something that is nice and simple. If it's not nice and simple, then we have to start calculating. And if it's especially messy, we can't even do it by hand. We need a calculator to do it. But sometimes you get lucky. Let's see about this one. How about if it is negative 2, comma 0? So again, this is the x, this is the y. So again, we can easily plot this, and then from plotting it, maybe we can figure out exactly what our position is. So here, once again, we can see that we're talking about a radius of 2 and a theta of pi. Now, so our theta equals 2, comma, pi. Now, I could have called that negative pi instead, or I could have called it 3 pi. The thetas here can be they can be very wide ranging, and our main goal, if nothing has been given to us as far as a specific range of answers, is just to produce whatever the most reasonable one is that pops into our head first. Okay, now let's take the point negative 3, comma 3. So we can actually see where we are on this one. We can see that we're in quadrant 2 here, and we can even see that since the x and the y coordinates are the same, this is actually one of the 45-degree angle ones. So we can actually tell what angle that is. So again, these are the x and the y coordinates being given to us. So we can tell that the theta here is going to be 3 pi over 4. Like that, we can actually just tell with the naked eye. We didn't need any formula or anything like that. Now, as for the r, to get that, we're going to use the Pythagorean Theorem. So r squared equals x squared plus y squared. And that's going to be r squared equals negative 3 squared plus 3 squared, which then is going to be positive 9 plus another positive 9 for a total of 18. So r squared equals 18, which means then that r is equal to the square root of 18, but 18 has a perfect square as a factor, namely 9, so that's 9 times 2, which is the same as square root of 9, square root of 2, which we can then rewrite as 3 root 2. So what does that give us then? It gives us r theta of 3 pi over 4, comma, 3 root 2. So again, we just looked at it and figured out what it was. We didn't have to use anything, any big formula for the theta. The r, we did have to use a formula. We had to use the Pythagorean theorem, but it wasn't so bad. All right, let's try another one. So let's say negative 2 comma negative 2 root 3. All right, so an important thing to note about this is it's negative and negative. And root 3 is bigger than 1, so that means that it's going to be further down than it is going to be left. All right, but this is again x and the y, and we'll just let the r and theta develop from the formulas. So r squared is equal to x squared plus y squared, which here means r squared is going to be negative 2 squared plus negative 2 square root of 3 squared. Now negative 2 squared, that's equal to just positive 4, plus over here we're going to have 4 times positive 3. The square would just distribute to those two pieces. And so in other words, we have r squared over here, and we have 4 plus 12 is 16, which means that r is equal to 4. And we're not going to bother ourselves with negative values of r here. Negative values of r are sometimes a necessary evil, as we'll see in the next section when it comes to graphing these, but they're not something that we go seeking out of our own free will. So r's can be negative, and that's just a technicality of the coordinate system, but it's not something we pursue. Now, so we will typically choose the positive one. So choose positive whenever you can. So technically, from here to here was a plus minus, but we didn't even consider the negative. Now, tangent theta is equal to y over x. So for the first time, we have to actually earn our theta. Before, we were just able to look at it and determine it. So let's think about what the y and the x would be here. Negative 2 root 3 over negative 2, which is just going to, those are going to cancel, and that's just going to equal root 3. But so this is a known value of tangent. We know that this means the steep slope version of the 60-90 or 60-30-90 triangle. But this is in quadrant 3. So theta is in quadrant 3, which means that what we thought was going to be our answer, what we thought is not going to be the right one, and we would want actually the other one. So that means this theta is equal to, if we were to do the inverse tangent here, we would end up with the positive version, and we would just have to adjust it by here. Let's just say radians. Let's just say we're working in radians here, and then we'll only use degrees when we're told to. So here, theta is going to equal. First off, this we think the answer is going to be pi over 3, but no, wrong quadrant. So then, in fact, it's going to equal. You can add pi, so it's going to be 4 pi over 3. So this is the wrong quadrant. And this is add pi. So at first we thought it was going to be pi over 3 from this statement right here, but that is not accurate. That's not the correct quadrant, so we add pi to put it into the right quadrant. So that's how we make adjustments for the quadrants. And then if we have just a generic point given to us that's not going to be one of our known things, then we have to bring out the inverse tangent function. So let's go with a final example from this category. So this is example E. And so let's say we have negative 2.3, comma 0.2. That's x, and that's y. Okay. So quick check of quadrant. Y is positive, x is negative, so we're over here, so it's in quadrant 2. Quadrant 2. Okay, well, nothing changes about our approach. The only thing that changes is that these don't become numbers we can just evaluate by ourselves. We need the help of technology. So what's this going to be? So 2.3 squared, we can ignore the negative because it's being squared. So plus 0.2 squared, and that's 5.33. And then we want to take the square root of that. So you can do square root, and then if you can find the answer button, it's usually somewhere near the equals second in that. And then that means that r itself would equal 2.31. Again, just by default, I'm going to round it to 2 decimal places unless told to do otherwise. So that's the r approximately. Now, tangent theta is equal to 0.2 over negative 2.3, which is going to equal 0.2 divided by negative 2.3. Just using calculator here to do all my dirty work for me. And that's equal to negative 0.0869, or so I don't want to round. So usually I've been rounding to 2 decimal places, but I don't want to round it to only one significant figure. That seems a little bit excessive. So I'll round it to that. But most importantly of all, really, I'm going to be just using the answer in my calculator so that I'm not actually using anything that has been rounded too aggressively. Okay, so then theta equals, this is the inverse tangent, So I'll now do the inverse tangent here. Inverse tangent. So tan inverse of both sides is what we're doing here, and that's going to be, I'm just going to use the answer. I don't want to round it if I can help it. Rounding too aggressively can make your answers a little bit bad. And notice we get actually a very similar answer to what we had here. It's an interesting fact. But when the angles are very small, then the radian measure of the angle is very close to the value of the tangent of the angle. So 0.087 radians. And then we look at this and decide, is this accurate? Well, this should be slightly over here. It is not accurate. We're in the wrong quadrant. So this is the wrong quadrant. Quadrant. It's in the wrong quadrant, so we can just add pi to it to bring it into the correct quadrant. So plus pi. This is our adjustment. For quadrant 2. And answer plus pi gives me 3.055. And here, by the way, when it comes time to give an actual answer, then maybe I will round it to whatever the specifics of the problem ask. It's only it's only while I'm still doing calculations that I want to make sure that I give as much precision as possible, so that my errors don't propagate through my further calculations. So just a quick note. The Pearson MyLab math homework will ask you to find a second value of theta so that you give all the values for not 0, negative 2 pi less than or equal to theta less than or equal to 2 pi. So what you'll want to do when you do this is just add or subtract 2 pi from whatever theta you got originally in order to put it into the other version. So just add or subtract 2 pi from your original theta. To get a second one, to get a second value in the range. So if by default you've been making your thetas positive, you would want to subtract 2 pi to get the negative version. And if by default you've been giving some negative values of theta, then you would want to add 2 pi to get the correct one. All right. Now, here comes the most algebraically intensive part of this whole section. So this next topic is converting equations. All right, so here's the basic goal here. The goal is start with an equation, so that means it has an equals sign and it's between two things. Start with an equation in one coordinate system. End with an equivalent equation in the other. And do not have a mixed equation at the end. It should be entirely rectangular or entirely polar, as the case may be. The result should be purely rectangular or purely polar, not a mixture. Okay. Now, here's the basic tools that we will have. The basic tools. So our basic tools. So what we will have are some equations, and those are the same equations that we know and love from earlier, and those will give us a dictionary for converting phrase by phrase from one coordinate system to the other. So x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared. And then finally, tangent of theta is equal to y over x. And in the way we can use these tools, so we use these tools to basically find and replace basic phrases in one coordinate system by the basic phrases of the other. And then sometimes that means we might have to do some manipulation of both sides of the equation in order to make it fit these patterns. So we use these by manipulating the original equation to produce expressions of these forms, which we then substitute into the other coordinate system. Now, once we have done the conversion unfortunately, our task is still not completely finished. So once we have converted the equation, we will then simplify it. As much as possible. And just a note, Pearson MyLab homework wants you to do a rather excessive amount of simplification, frankly. But in addition to that, it wants you to move everything at the end to one side so that it equals 0. Pearson MyLab homework wants you to format your final answer in the form blah 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 equals 0, or 0 equals blah blah blah. And this just means move everything to one side. The Pearson is a little bit inflexible in the style of answers that it will accept, and it's actually I think excessively restrictive on the answers that it makes you provide. But oh well. Okay, actually here, we should note what when I say simplify as much as possible, what that means here. So simplification that we have to do. The simplification that we have to do. So we will have to sometimes use trig identities. Or algebraic techniques. To make the answers as nice as possible. In particular, one thing we want to try to avoid, if we can, would be something like square roots. So we can remove square roots when possible. And that would be accomplished by squaring both sides. You might have to move everything to one side and then square both sides. Do something like that. Remove square roots when possible, and also apply the double angle formula, which is, and the one that we're going to be using is the sine one. So this would be cosine theta, sine theta. Two times that is equal to is equal to sine 2 theta. So this is the double angle formula from section 6.6, and we will apply that to remove expressions like cosine sine. Okay, well, let's just try this. So first example here, let's say we're going to convert to polar coordinates. So convert the equations from rectangular coordinates to polar coordinates. All right, so the equations that we're going to be starting with are always going to involve x's and y's. The equations that we're going to end with will always involve r's and thetas. And so that's the game. So let's start with this one. So 2x squared plus 2y squared is equal to 3. All right. Well, here, if I pull out the 2, I'll get a very familiar looking expression, x squared plus y squared. So then here, perhaps what I will do is I will just write this as 2r squared equals 3, which maybe I would want to write as r squared equals 3 over 2. If I wanted this to be completely solved for r, and I took the square root of both sides, then that would give us root 3 over 2, which maybe then I would then rationalize the denominator of that. Also, I can rewrite this as r squared minus 3 halves equals 0 if I want to put it into the form that Pearson likes. And the format that the Pearson would prefer will depend a little bit on what type of a problem it is. Oops. Some problems it gives you a multiple choice. Sometimes it makes you type it in. And with the multiple choice ones, it's ironic. There's a little bit more flexibility in how they can be arranged. For the ones that you have to enter the answer, it can be a little bit more restrictive. All right. I was just trying to make a separation. I accidentally started to cross that out, so I rewrote that over there so that it wouldn't look like I was dismissing it. Okay, let's try another one here. So x squared plus y squared equals x. So once again here, we actually have a very convenient setup for just doing a straight up conversion from what used to be the rectangular coordinates into the polar coordinates. Right here, we can easily see that's just going to be r squared on the left, and that's going to equal r cosine theta on the right. And now here I can divide both sides by r, and I get r equals cosine theta. And that would be a nice simple answer, or r minus cosine theta equals 0. And that's just depending on whether you are doing this for me or for Pearson. Either one of these would be fine for for me, and this one would sometimes be the only one that the Pearson would like. Okay, let's see what else we can do here. How about something like x squared equals 4y? Well, if this were x squared plus y squared, I know what I would do. If it's just x squared, then what I'll just do is basically just take this as it is and just replace everything by what I know them to equal. So this is r cosine theta all squared, and that's equal to 4 times r sine theta. And now I would just distribute the square, and I'd have r squared cosine squared theta is equal to 4r sine theta. And then that you can just move everything to one side if that's what Pearson wants you to do. R squared cosine squared minus 4r sine theta equals 0. So that's how that would go. Now let's see. Another example, one that might require a little bit fancier trig identity. This is E. Let's say we had something like 2xy equals 1. Well, let's just see where that would give us. So 2r cosine theta r sine theta equals 1. And now let's just look at what equation that would lead us to. So it's two copies of r, so it's going to be r squared cosine theta sine theta equals 1. But this is, as previously mentioned, the double angle identity. Sine 2 theta is equal to 2 cosine theta sine theta, or sine theta cosine theta, however you want to write it. So then that means this is just equal to r squared sine 2 theta. And that equals 1. And then maybe I just move everything to one side. R squared sine 2 theta minus 1 equals 0. And maybe I have an equation like this. Maybe I have just x equals 4. So if x just equals 4, then there's not really much I can do here other than just switch out x for r cosine theta. And then maybe I have to move everything to one side to satisfy some robot. So there's a sample of the kinds of equations we can have that start off being in rectangular coordinates and end up being in polar coordinates. They tend to be a little bit on the straightforward side because you can always just take every x and swap out an r cosine theta, and take every y and swap out an r sine theta, and that'll usually get you most of the way there. But now let's try an example that goes the other direction. Convert the following equations from polar coordinates to rectangular coordinates. And let's just start with something like this. So A, r equals sine theta. All right, well, if this had been an r squared, I have an easy way of translating that. So maybe you think, oh, I could square both sides to make it fit our little list of formulas. However, that would leave us with a sine squared theta. And we don't have any formulas that involve a sine squared theta. In fact, we don't even have any formulas that involve just straight up sine theta that are purely rectangular. So the best thing we could do here is manipulate this by changing both sides into something that we're more comfortable with, and that would mean multiplying each side by r, because that makes the left side r squared, which we know what to do with, and that would make the right side equal to r sine theta, which we also know what to do with. So we multiply both sides by r, multiply by r to make the expressions match our formulas. Okay, so then what's that going to be? R squared equals r sine theta. In other words, x squared plus y squared, so this is just the Pythagorean theorem, equals y. And then if I wanted, I could just rewrite this in perhaps x squared plus y squared minus y equals 0. Let's move everything to one side. So that's nice. What about something like this? R equals sine theta plus 1. So that plus 1 is a slight twist on the whole thing. And if we think about this, what we're going to have to do here is, if we want to avoid anything unusual, any kind of weirdness, we're just going to have to see what we can do as far as making this now fit a pattern that we know. So let's see how this can work. So this is r equals sine theta plus 1. That's what we're starting with, and let's just do what we did before, multiply both sides by r. R squared equals r sine theta plus r. Now, these terms are all pretty good, but this term is actually not yet right. It doesn't fit our known patterns. So here, I might go ahead and make like a mixed equation along the way here in order to make my progress a little bit clearer. So I need to deal with that. So I wish that were r squared. We wish this were r squared. So when you wish something like that, one thing you can do is move everything to the other side and then square it. Square both sides. So then we'd have x squared plus y squared minus y equals r, and then we could square both sides. X squared plus y squared minus y, that whole thing squared, is equal to r squared. And then finally, we'd have that x squared plus y squared minus y all squared equals x squared plus y squared. So this would be that expression. If I wanted to, I could FOIL this out. There's not really a good reason to do that, though. if I move both of these terms over to make it fit that pattern, that's what it would look like. Now you can see here, the algebra in these ones can be a little bit more intense than it was in the other direction when we were converting from rectangular to polar. But that's what happens. Math is usually an unbalanced affair where one side of the operation is easy, the other side is harder. Okay, so let's now look at another example. R squared equals cosine theta. R squared equals cosine theta. All right, well, once again here, if this were r cosine theta, I would feel a lot better about the whole thing. Unfortunately, there's not a good way to make this an r cosine theta without making me feel worse about the left side. But that's what we'll do anyway. This is r to the third now is equal to r cosine theta. Okay, so now we're totally satisfied with this side, relatively unsatisfied with that side. It doesn't really fit any of our patterns. If this were something that involved an r squared, it would. So here's the trick on this. So now we square both sides. Square both sides. So that the left can be written as r squared to some power. Okay, because then we would be able to convert it. So we square both sides. And that's going to mean r to the sixth on this side. And then r squared cosine squared. Actually, better yet, I'll just leave the left. R cosine theta squared. And this is the same as r squared all to the third power. And that's the same as r cosine theta squared, which now we can finally convert this to x squared plus y squared all raised to the third power is equal to x squared. Now we move everything to the left if we are doing this for Pearson. And that would give us this minus x squared equals 0. So that's what we have to do in one of these. This is essentially a worst case scenario here. So there's the worst it can get. Now, other things that we can see would be equations that look like this. So this was example, sorry, that one was example C, so this is D. Let's say we have just something like r equals sine theta plus cosine theta. Okay, so this one's much easier than the previous one. What do I want? I want everything to be slightly different, and the way I want them each to be different is I want them all to be multiplied by r. I want that to be an r squared, I want that to be r sine theta, and I want that to be r cosine theta. So I'll just multiply by r. And when I multiply by r, I have to multiply the entirety of both sides. That means both terms on the right. So that gives us r squared on the left equals r sine theta plus r cosine theta on the right. And then that means x squared plus y squared is equal to y plus x. And then if I want to move everything to one side, x squared plus y squared minus y minus x equals 0. Okay, now what if we have something like this? Maybe we just have an expression like r equals 3. Well, we have an r. We wish we had an r squared. The right-hand side is just a number, so that doesn't require any kind of special treatment. So let's just think about what we can do here. We could just square both sides. So r equals 3. So just square both sides. And that would have r squared for the left and 9 for the right. And then finally, x squared plus y squared equals 9. Or in other words, x squared plus y squared minus 9 equals 0. All right, what about something like this? And so notice, by the way, r equals 3. This is a circle of radius 3. And then this would be the equation of a circle in radius 3 in rectangular coordinates. But we'll discuss that more in section 8.2. So just a heads up. All right, now how about theta equals pi over 3? Theta equals pi over 3. So this is an equation that gives us just theta equals some value. This first one, or the previous one, just gave us r equals some value, which means that we're talking about a radius 3 circle. Here, we're talking about a ray, or I guess a line, at pi over 3. And that is going to just be going up that way, like that. So we can tell it's just going to be everything whose direction is pi over 3. When r is positive, it'll be in quadrant 1. When r is negative, it'll be in quadrant 3. But that's the general layout here. Now, as written, it doesn't fit any of our patterns. But if I were to take the tangent of both sides, then what I'd have is tan theta equals tangent of pi over 3. And so then that gives me y over x is equal to tangent of pi over 3, which is the square root of 3. So in other words, y equals root 3x. Now when I said get rid of square roots, I really meant square roots on our variables. I'm not so offended by square roots on that are just constants. Root 3 times x equals 0. So this is a line with slope root 3, which makes perfect sense when you think about what theta really means and what it means for theta to be fixed at a certain value. It means we are on a line whose slope is the tangent of that angle. Tangent basically converts between slopes and angles. All right, now for our last example in this section, the last of this category. Let's see, this is F, so this is G. Let's say we have the equation r equals 3 divided by 3 minus cosine. 3 minus cosine theta. Okay, well, let's look at what we've got here. So we want to try to express this in more familiar terms. So let's start by just multiplying both sides by that denominator right there. So what's that going to give us? So 3 minus cosine theta and 3 minus cosine theta. Okay, so that'll cancel. And over here, we'll have to distribute. So we're going to have 3r minus r cosine theta equals 3. All right, well, we can see that we are in the same situation that we were in a bit ago when we had our r wishing that we had an r squared. So what we can do here, now we don't want to mess with this. This one is already perfect as is. So what I'm going to do is I'm going to isolate the r, or at least the 3r, and I'm going to square both sides. I'm going to add r cosine theta to both sides. That gives us 3r equals r cosine theta plus 3. And now I'll square both sides. And so that means that we're going to have 9r squared equals r cosine theta plus 3 squared. Now, everything that I'm looking at this point is pretty convenient for converting to rectangular coordinates, so I will now go ahead and do that. So 9x squared plus y squared is equal to quantity x plus 3 all squared. Now, if I wanted, I could distribute this. 9x squared plus 9y squared is equal to x plus 3 all squared. Now here, if I wanted to rewrite this as all FOILed out, I could. So if I FOIL this out, it's going to be 2 copies of x plus 3, so it's going to be 6x for the middle terms and 9. And so then what we're going to have here is 9x squared plus 9y squared minus x squared minus 6x plus minus 9 equals 0. And then those two are like terms that can be combined, so that's going to be 8x squared plus 9y squared minus 6x minus 9 equals 0. So that would be that. So this is again about as bad as it gets. These are some complicated expressions we've got here. And part of what makes them so complicated, actually, is the rigidness with which the homework module requires you to format your answers. So it's not always going to be the case that we will be interested in simplifying as far as this. It's only when the homework module requires it of us. Now the last thing we're going to talk about is section 8.2, in which we will briefly talk about the graphing of polar equations. So polar equations and graphs. So the basic thing to know here, is that a polar equation can be graphed in a way that is kind of analogous to the way rectangular equations can be graphed. So note, we can produce graphs of polar equations when the R has been solved for in terms of theta. All right, so there are two main categories here. There are a very small number of equations which are given in polar form, but actually are easier to understand by converting them into rectangular form. So the first category is 1, polar equations that are easily changed to rectangular equations whose graphs are obvious. And the main category of these are lines. So these will often just be lines. So lines are typically the easiest graphs to produce in rectangular coordinates, and this will be the main category of polar equations, where our default response will be to convert it into a rectangular equation instead. And then the second category is the category of polar equations that are easiest to understand as polar equations themselves. So these are polar equations that are easiest graphed by considering the way the R changes as we input different theta from 0 to 2 pi. And this will be all the rest that we'll usually consider in this section. So, category 1. So let's just first talk about, let's say, just horizontal lines. And the way these look is something equivalent to this. So x equals just some a, sorry, y equals just some a, I should say, for a horizontal line. So that would be the rectangular form. And then the corresponding polar form would be r sine theta equals a, or r equals a over sine theta. Occasionally you might see this written as r equals a cosecant theta, but that'd be pretty unusual. Usually when we're producing graphs, we stick with the functions that are easiest to work with, and that would be sine and cosine. Vertical lines, on the other hand. So y equals, now it's x equals a. And so that would be r cosine theta equals a, or r is equal to a over cosine theta. So those are the two main categories of just sort of lines other than lines through the origin. And then there is the category of slanted lines through the origin. So then the format of this is y equals just mx, and b here would be 0, so just have this form, which means that r sine theta is equal to m r cosine theta, which then means if we were to divide both sides by r, that'd be sine theta equals m cosine theta. And then if we divide both sides by cosine theta, we get tan theta equals m. Tan theta equals m, or occasionally we would just write it as theta equals, and it would be the inverse tangent of m. And in other words, theta equals just some angle alpha. And here, what this would mean was we would have just some line going through the origin. The angle of it would be alpha, which equals the inverse tangent. Actually, here the easiest thing would be not to write it in terms of inverse tangent, because that gets a little tricky depending on the quadrants. This would be the easiest way. And then the slope would be the tangent of alpha. So as an example, let's say theta equals pi over 6. So that would be a line that is made up by taking the slant that goes through the origin, slope pi over 6, it looks like that. And the equivalent line in rectangular coordinates would be y equals inverse tangent pi over 6 times x, which would be equal to root 3 over 3x. So the slope here would be root 3 over 3. Okay, so these are the main categories. Now let's look at category 2. All right, let's start with circles. Circles. So circles. Centered at origin. So if they are centered at the origin, the equation is just going to be r equals some constant, a. And this equation would define the circle whose radius was always a. So it would mean we're talking about the set of all points where the distance from the origin is always a. Now there are a couple other special kinds of circles, and these are circles that have been a little bit altered. So these all just come from the fact that what we have here, no matter what theta we put in, it's just going to be the same value of r. So if we have r equals a cosine theta, then let's just think about that. So this is going to be a circle where when theta equals 0, when theta equals pi over 2, when theta equals pi, when theta equals 3 pi over 2. So this is going to be a circle that's defined by taking the whatever the cosine is at each of these angles and being that far away from the origin when we're there. So for the very first point, when we plug in 0 into cosine, that produces a 1. And so then this is going to be way out at a. Now let's think about as cosine sweeps around here, the x value is going down, which means then that the distance from the origin is going down, and in particular, it goes from 1 down to 0 by the time we get here. And then at pi, that's when cosine starts to become negative. And so instead of being down in this quadrant like it should be, what happens is we actually start producing a negative radius. When over here, cosine starts being negative. So instead of being in the quadrant it's supposed to be, it's got a negative radius, so it reappears down here, and it looks like that. Or there's r equals a sine theta. And again, you can just start thinking about it, reasoning it out. What happens when theta is 0, pi over 2, pi, and 3 pi over 2? Okay, so it starts out with a radius of 0, because the sine is 0. Now, as we start to swoop around, the radius is getting bigger and bigger and bigger until it reaches its maximum over here. And that's at A. And then that's when it maxes out at 1, so then times A. And then it goes back down to 0. And then at this point, as soon as it enters quadrant 3, the sign is negative, and so it actually appears over here, and it actually traces this out again from the other quadrant. So that's what's going on here, or over here, and then goes around basically twice. All right, and then another category of polar graphs that we can look at are what are called limaçons. And that's a C with a cedilla. and cardoids. Lemmasons and cardoids. All right, so what these two words mean are snails. This is an old French word for a kind of snail. And heart-shaped. All right. So here's the formula. The formula for this whole family of curves is something of the form r equals a plus or minus b sine theta or cosine theta. And it's the values of the a and the b that will determine which of the shapes it will be. And it's whether it's plus, minus, sine, or cosine that will determine the orientation of it. So let's just look at how this would go. So first off, cardoids. This is when a equals b. A equals b. So let's just have, for example, let's say r equals 2 minus 2 cosine theta. So the best way to do this is you just think about different values of theta around the circle and what those would do to the cosine. And then you just figure out what that would mean if that's the radius. Okay. So when theta equals 0, this will equal 1, which means the r will be 0. When theta equals pi over 2, this will equal 0, which means the radius will equal 2. When theta equals pi, the cosine will equal -1, which means this will be equal to +4. So the radius will be 4, which means it'll be 4 out from the origin. And then when cosine is equal to, sorry, when theta is equal to 3 pi over 2, the cosine will be 0, which means the radius will be 2 again. Okay, so what's this going to mean? This means that as we sweep around from 0 around and around until we get to 2 pi, we're going to be going out to there, out to here, back into here, and then back into there. And these ones are technically going to be negative and negative because that's how. So it's going to go around, going to go around, going to go around, and it's going to go around. So that's what cardoids look like. And again, it's the cosine versus sine and the plus versus minus that will determine the orientations. Now, lemmasons. This is what happens when we have A bigger than B, or this makes it without inner loop, or B is bigger than A, and this means with inner loop. You'll see what that means in a second. So let's just see two examples of that. One where A is bigger than B, and one where B is bigger than A. So A bigger than B. An example of something like that would be R equals 3 plus 2 sine theta. So let's just think about what this is going to mean. So 0, pi over 2, 3 pi over 2. Just pi, I should say. Pi, 3 pi over 2. And then let's just think about what the r's would be here. So the r here is 3. The r over here is going to be, so we plug in theta equals pi over 2. That'll make sine equal 1, which will make this equal 2, which will make r equal 5. Over here, when we get to this, the sine will be 0 again, so the r will be equal to 3 again. And then over here, this is when the theta will be at 3 pi over 2, which means that the sine will be at negative 1, which means that r will equal 1. And this will be its minimum value of r. So this is kind of like a cardioid, except that it's not a heart where so this one's heart-shaped with the little cusp of the heart at the origin. This one will not be quite heart-shaped. It will be instead snail-shaped. I don't quite see the resemblance, but it's an old name for a shape, and I will leave it to the French to decide what the proper shape of a snail is. They would know better than I. All right. So this is no inner loop. And then one where there is an inner loop would be something like this. Well, we'll just switch it. So 2 plus 3 sine theta. This is no inner loop versus one where it does have an inner loop. Let's see what that would mean. Okay, so this gets a little bit tricky. So let's be very careful here. Okay, when theta equals 0, this will be 0. So this means the radius will be 2. When theta equals pi over 2, this will be 3, which means the radius will be 5. So far, nothing different. Over here, I mean, it's slightly different numbers, but not different in principle. Theta will be pi, meaning sine will be 0, meaning the radius will be 2. And now here's where it gets tricky. On this one, the radius is going to be, so this will be negative 1, make that negative 3, make that negative 1. Now that's the tricky part, is trying to draw it when the radius turns negative like that. Because that means instead of being in the quadrant you think, it's going to be off to here. So somehow it goes through the origin out to the other quadrant. So that's what's going to produce what's called the inner loop. Okay, so let's say that's 2. Let's say that's 5. Let's say that this will be negative 2 over here. And then this one somehow goes up and then group like that. So let's just try to draw it. And we'll cross that bridge when we come to it. So it doesn't look so different on this part. It's this other part. So what happens is here at some point in this quadrant, at some angle, it gets through, like radius becomes 0, and then it's less than 0, and we get the inner loop right there. All right. So that's another category. And then the last category that we're going to talk about are what are called lemniscates and roses. So lemniscate is an old Greek word that means ribbon. And as for roses, it's as in the flower. And the idea is both of these shapes produce, both of these types of equations produce graphs whose shapes have petals like a flower. So lemniscates. So the formula is going to be r equals the square root of a sine 2 theta, or r equals the square root of a cosine 2 theta. And the graph, what it produces is something that looks like this. Or something like that. And this is for sine specifically, and this is for cosine. And we'll graph it. It's a little bit tricky to graph these because their formula is more complicated than usual. So we'll graph using Desmos. I'll show you how to do that in just a second. And then for roses, the formula is of the form r equals a sine n theta, or r equals b, not b, still a, cosine n theta, where n is an integer above 1. And then the graphs of these look like this. So what you could have is maybe one with 3 petals. You can have one with 4 petals. Etc. And if n is odd, n equals the number of petals. If n is even, n equals number of petals times 2. So the number of, sorry, I don't mean that. I mean to say number of petals equals n times 2. So the value of n will determine how many petals there will be. If it's odd, it will be the number of petals. If it's even, then 2 times n will be the number of petals. All right, so let's go over to Desmos and see what this looks like. Oh, and I'll just say graph using Desmos, so it's on the record. And the reason why we have to graph it using Desmos rather than just sketching it out the way we did the other ones is because having the n in there means that we are not just going around once when we are looking at the theta, but it's actually going through the sine and cosine cycle multiple times as we go around, and that makes it just a little bit more complicated to graph. All right, here we are. I brought up Desmos. Let me show you how to do polar graphs on it. So by the way, first off, you can change it to projector mode to make a bigger or bolder graph. And now on the grid, you can change the grid format from the rectangular grid to this polar shaped grid, which shows you certain key spaced out angles around the plane. Now, the way you enter a graph or enter a formula in Desmos is you just put little r equals and then whatever the formula is. It can't be r squared and it can't be like r cosine theta. It has to just equal r. And here you could have like r equals 5, r equals 6. And you'll notice these are producing graphs that make circles of radius 6 or 5 or what have you. You can make r equals 2 divided by sine theta, which, as we already saw, is a horizontal line. You can also put in some of those other graphs that we've seen. One thing you can't do, though, is you can't do the line like theta equals pi over 6. So that doesn't quite work. If you want to do that kind of a line, you have to do it in the form like y equals. And then here, it would have to be whatever the actual slope turned out to be, which would be the tangent of pi over 6 times x. So then that produces that line. So you can't do those straight lines through the origin in polar coordinates on Desmos. It always has to be r equals whatever. Okay, now let's see. What about r equals 3 sine theta? So there what we have is a circle, just as we knew it would be, or cosine theta. Oh, by the way, what we saw right here, this is a spiral. This happens because as we go around and around the circle, the r would be getting bigger and bigger and bigger, and it produces it was called an Archimedean spiral. Okay, now let's see other ones that we know. So let's make a graph of a limaçon. So what we need are two numbers, a and b. First, let's say they're the same. 4 plus 4 sine theta. Okay, so this makes the cardioid version of a limaçon. And so notice it's like a heart shape. And what makes the difference when we change this from plus to minus is just the orientation. Oops. What makes the difference if we change this from sine to cosine is, again, the orientation. So that's the effect of each of those, but the overall shape is the same. Now, if we make this number smaller than the other number, so if this becomes a 3 instead of a 4, then what we get is a limaçon without an inner curve. And again, or an inner loop, I mean. And again, changing these things around just changes the orientation of it, but it doesn't change the shape of it. Okay, and then if, on the other hand, this number is bigger, if the b is bigger than the a, that's when you get the loop, the inner loop. And the bigger the difference, the bigger the inner loop. Oops. And so if this was 8, our inner loop would be bigger still. Okay, now let's look at lemniscate. So square root, SQRT is the easiest way to get that in on Desmos. SQRT for square root. And then let's say 2 sine 2 theta. So that gives us the little ribbon shape. It goes like that. Make that into a cosine and you make yourself a nice little infinity shape. Very pretty. Okay. Now for roses. So let's say we have 2 sine, first just theta, And that is just a circle. But we make this a 2 theta. And it becomes a rose with 2 times 2 petals, 4 petals. 3, because it's an odd number, it's going to be an odd number of petals. It's going to be just 3 petals. 4, this one has 8, 5, and so on. So there you go. This is how you can make roses in Desmos. All right, well, that's going to do it. Sorry, so actually let's talk about what your Pearson homework is going to be like for this section. So for this section, you're going to have a matching problem where you're going to have a variety of different equations in polar form and a variety of different graphs, and you just have to match them. And some of them will be quick and easy because there'll be some vertical lines, horizontal lines, circles, things like that. And some of them will be a little bit more challenging. There'll be maybe limaçons, and you just have to figure out what goes with what. And if you are in doubt, you can always graph it on Desmos and see from that. All right, that's going to do it for this session of Math 112. So I'll see you next time. Bye.